Hello students, so in this lecture we will be discussing about workability. Now workability is concerned with the extent to which uh, the material can be deformed. Extent of material deformation. And by deformation we mean that there is no uh, formation of cracks. So we are mainly talking about the plastic deformation when we say deformation in case of workability. Now, the limit of workability is can determine by the formation of local necking. Necking, as told previously, is the reduction in the cross-sectional area in the gauge region. So when there is a reduction magnified this, so a reduction taking place in the cross-sectional area, this is the process of necking, and it is the onset of plastic deformation. Now, workability is a complex technological concept. It depends not only on the fracture resistance, uh, that is ductility. A more ductile a material is, the more is it resistant to fracture. So it's fracture resistance. A more workable a material is, the more resistance it has towards fracture. Now there are also other aspects to workability. One is the material dependent, and that is the experimental or the test conditions. These two factors govern the workability of a material. Like, so in the deformation process, the material is being deformed. So we can classify the parameters as two different functions, f1 and f2. F1 depends on the properties of the material. It's material properties. While f2, these factors, they depend upon the deformation process or the parameter used in the deformation process. Meters in the deformation process, and these parameters are the die geometry, lubrication, geometry of the specimen and the workpiece, Now, the cracks that occur in a metalworking process can be grouped into three broad categories. So, workabilities where we are not expecting any cracks to occur. Still, during the working or during the deformation of a metal, there are formation of cracks which are not desirable. And these cracks, they occur and they can be categorized into three different types. The first one is the one that are occurring at the free surface. That is a bulge in an upsetting cylinder or an edge or in rolling. Second type of cracks that occur where there is an interface friction is high. And there is an interface friction is high, like in the case of an extrusion. And the third one are the internal cracks in the sample which are pre-existing, like chevron cracks. Right? So these are the three categories in which the cracks can be divided. Now these cracks are the internal cracks, for that matter, material dependent cracks which are initially present. Internal cracks are developed as a result of secondary tensile stress. Secondary tensile stress, where you have a large aspect ratio, like when the height L, height versus length ratio is large. Secondly, we have when temperature gradients, and like when a workpiece is is chilled by a die, since the flow stress is very much a function of temperature, dependent upon temperature, for that matter. So a place where the temperature is very low, that is a chilled region, temperature is very low. So as the temperature is low, so flow stress or the flow of stress, the dislocation movements are hampered. So it actually causes something called a local non-deforming region. A local non-deforming zone. Now, in contrary to that, there are places where uh, the temperature is not so chilled or and hard, and easy flow. These are the two different regions which can exist due to differences in temperature, and these regions in fact lead to the formation of shear bands. Shear bands, which actually leads to something called shear fracture. Another place where these shear bands can be seen is during the process of an indentation where you have a sample. If you want to know the hardness of the sample, you indent it with a tip of definite geometrical shape. It can be Vickers, it can be Rockwell, Brinell, or sometimes Berkovich. So they all have different geometry of indenters, and let's say for the case of the Vickers indentation, you get an indent like this, and the hardness is measured by measuring the diagonals D1 and D2, and the Vickers hardness is then expressed as equal to 1.854 load applied divided by D square, where D is the average of these two. Now in this case of Vickers hardness, Vickers indentation, the shear bands are also visible. Like if this is the indentation that is formed, you can see shear band formation surrounding it. So this is another place where shear bands are observed. And they are regions of high strain and often leads to fracture. Like in the case of indentation, however, you get radial and lateral cracks, which are examples of fracture that has taken place. Now, ductile fracture may be also responsible for the formation of crack. Material under tensile stress, if it is a ductile material, so it will ultimately neck and it will form, it will separate. This is known as a ductile fracture. However, if it is not a ductile material, then there is no question of taking place, and the material will simply crack down like this. So this is called a brittle fracture. So Usually, metals, they undergo ductile fracture. Brittle fracture is more in the case of a ceramic. Now, this ductile fracture uh, they are characterized by formation and growth of holes around second phase particles. Formation and growth of holes or voids around the second phase particles. Second phase particles. And the localization of strain is sharply defined bands. Second aspect is that there is a localization of shear strain and this localization takes place in sharply defined bands. Now, one can also observe formation of voids in ductile fracture. And these voids are associated with plastic instability of making. Plastic instability of making. Now, to predict workability, a fracture criterion for ductile fracture must be established. The most general applicable ductile fracture criterion is the proposed by Cockford and Latham. So, it's the ductile fracture criterion fracture criterion, and it was proposed by Cockcroft and Latham. And according to them, that this ductile fracture will be based on some combination of stress and strain, and that can only the highest local tensile stress will be important. So when there is a ductile fracture that has taken place, so normally there will be a lot of stress and strain at the local level, and out of which only the highest local tensile stress given as sigma star will be of any concern, will be taken into consideration. And so according to this criterion, this sigma star, the average strain is a constant, and integration has been done till the strain at which the fracture takes place. And it is valid for a given temperature and strain rate. Now, the ratio of these strains is varied by changing the d by diameter versus height ratio of the specimen, and the frictional concept for cylindrical specimen under compressive stress. Now, as we have previously mentioned, that there are two factors, one F1 in the workability. F1 factors are called the material factors, and F2 factors are the process factors affecting the workability of a material. So based upon all these things, a workability limit diagram has been can be proposed. It's called the workability diagram can be proposed. So this is the workability limit diagram. it's better to now what the workability limit diagram, if you expand this, you have a compressive strain in this axis, and you have tensile strain in the y-axis, and this line represents the natural log of diameter versus this height ratio. So there are two materials into consideration. So this is called the material A, and this is called the material B, and these are the different strain paths for the two cases. The different strain paths. Now these strain paths are determined experimentally by placing rigid grids on the surface of a model. Now what is shown in this figure is you have a sample like this, say of diameter d. It has been under compressive stress, and secondly it has been, you have a shape like this, a bolt head with a diameter d. Now to form a head of diameter capital D from a rod, so a rod of diameter D is being pressed to form shape D. So there is a change in diameter from small d to capital D. Now, so the strain path must reach this limiting value of strain without crossing the fracture limit. So there should not be any fracture. So the fracture limit must not be crossed, not to be crossed in this case. Now if you look closely into the diagram that we previously have shown, the first case where it is being shown this sample, this path does not meet this criteria, okay, because this is the fracture limit. So it is has gone above this criterion. However, the strain path for the sake of sample B, this actually is maintains this criterion. Okay. Now, so what can be done by improving the lubrication? What can be done here is the lubrication can be improved during the workability. To shift this curve path B, and to form a diameter d from small diameter d. So this workability concept is useful in the case of forging of metals.